Right, so how do we get angle alpha in the picture? It looks to me like the easiest way to understand alpha is to think about it again in the context of a triangle, right? So if you think of the angle sum of, now which triangle should I use? I want a triangle which has theta and has alpha in it as well, right? So there's theta and there's alpha, right? So therefore, what's this angle up here?
Pi minus alpha minus theta.
Yeah. Okay. So I'm going to write that all out. Okay, because that's going to be my bridge into this identity. Because I want an alpha plus theta as well. So I'll say, let's see, theta plus alpha plus that angle, CPO. That's equal to pi radians because of angle sum of a triangle, namely that one, right? So like you just told me, CPO on its own will be pi minus those two angles, okay? Which is suspicious, okay? Okay, good. Now have a look at that triangle. At the moment, it's nothing special, okay? But they say at a particular point, right, when theta is equal to, and I think they say, is it pi on 2?
Oh, that's just the part.
Oh, am I getting ahead of myself? Oh, that's right, of course. Yes, that is getting ahead of myself. I don't know what theta is at the moment,
Yeah.
which means that I can't assume anything about this triangle, right? But this identity that I've got, it has signs in it, right? And I can put signs into any triangle, not just right angled triangles, if I use the sine rule.
Yeah.
Okay. So let's do that, right? Now I've got sine alpha, right? I can see sine alpha. It will be opposite what sign?
1.
And it'll be so OP, which is 1,
Oh, okay.
right? Which is fine. It's okay. When you're doing the sine rule, you want to make the sine ruleness of it as obvious as possible. So don't put in numbers until the very end, right? And then this angle here, right? Because again, it's going to allow me to use a sneaky identity to get to here. Okay. So sine of angle CPO over, now what's it opposite?
OC.
OC, which we also know.
Yeah.
Okay. So you've got your sine alpha on 1, your sine of this awkward angle in here, pi minus alpha plus theta on 2. That's suspicious, right? Now, you do have to show, right?
Yeah.
This result is given, so you can't just write it down because you're like, well, I haven't shown anything, okay? So the way I would say it is, just to jog my memory, I'm like, look, this is what sine looks like between 0 and pi. Okay, I'm not going to bother drawing the rest because I don't need the rest. So if I've got alpha plus theta as some angle, okay, let's call that alpha plus theta, okay? Clearly, sine of pi minus that angle, which is pi minus that angle, the sine values are the same, okay? So therefore, I can say, this is sine alpha. I can say, maybe I would put it here, but sine of pi minus some angle is the same as sine of that angle, right? So I can substitute that for sine of alpha plus theta, which is what I'm after, over 2, and then you just put the 2 over the other side and you're there. Theta. No, alpha. Right, the first time. Okay, is that right? Okay, now I can't. Let's see. I need space, but I can't rub out too much. What am I going to do? I'll try and go over here,
Yeah.
if that's all right. This is not so important. You saw the logic behind it. Okay, part 3. Now we get given a specific value of theta. So we're given a particular instant in time. Okay, so it's when theta equals pi on 2. Is that right?
Yeah.
Yep. And we're asked to find. What are we asked to find? Let's see here.
Angular velocity of-
Okay, yeah. We want the angular velocity of this guy, right? In other words, how's he changing with respect to time? Okay, so I'm after d alpha on dt, or if I want to be, to follow this convention, I'm after alpha dot, okay? So, that's what I want to get to. Now, here is my one and only equation that tells me anything about alpha and how it changes, okay? So you need to remember from here, right? Theta is a function of time, it's changing. Alpha is a function of time. It's changing, right? So you can deal with this line, which has alpha in it. I want to get to alpha dot, so clearly I'll need to differentiate this. Okay, I'll need to differentiate this. Now, remember that alpha is a function of time, theta is a function of time. So this whole thing in here is another function of time.
Yeah.
Okay, so in fact, this whole thing is really all with respect to time. So I can differentiate the whole thing with respect to time. Okay, so I've got this sort of in my back pocket, which I'm going to use in a second. I'm going to differentiate everything with respect to time. And I like to put this down, not because it'll get you any marks, but so that I know what I'm doing, right? So I've got 2 sine alpha. All right, let's give this a go. Now, because these are all functions, this is chain rule, isn't it? Okay. So when you differentiate this part here, you differentiate the inside, and then you do the outside. Okay. Now, these are both functions. I don't know what the functions are, but I know what their derivatives with respect to time are. It'll be alpha dot and theta dot.
Yeah.
Okay, so that's good. That's what I'm after. When I differentiate the outside, sine turns into cos. Cos of alpha plus theta. Okay, this 2, I'll just kick it out the front because it doesn't matter. Again, it's chain rule because alpha is a function, so I'll get alpha dot. And sine turns into cos again. Okay, so that's good.
Oh, and the 2.
Oh, right, sorry. 2 at the front. Okay, cool. So this is really good because I've got alpha dots in place, right? I've got theta dots, but I can get rid of theta dots because I know what theta dot is, right? So let's do it one step at a time. I've got my alpha dot there. I know what that is. It's pi. And then when you go to here, you're like, hold on. Theta has a particular value. So this should be alpha plus pi on 2. Okay. And then you've got 2 alpha dot, and then you've got cos alpha. Okay. Now at this point, you kind of scratch your head and you think, I've got these alpha dots, which I want, and then I've got these, which I have to get rid of somehow. Okay. So you're like, how do I get them out of the picture? Okay. Well, one step at a time. Let's think about the easier one first, the one without the phase shift in it, cos alpha. So how do I get cos alpha? Well, if I want to know the value of that, then I need to know what alpha is, right? Or I need to know where it's situated. Now the thing is, this diagram, right? It's a general diagram. It's at any instant in time. But I have a particular instant in time in mind. So I will draw a diagram of this for that value, okay? So it's going to look like this, I'm guessing. Here's my circle. I've got my AB, right? And then here's, that's a bit too far, isn't it? I've got C, and I'm going through the origin. Now, where is theta, which should be pi on 2? And the answer is it's this angle in here, and it's a right angle.
Yeah.
So there's my theta, right there. So now I've got this triangle in here, right? But I know that this, right at the beginning, that's 2. This is the radius, that's 1. Where's alpha? It's here. So cos alpha is adjacent on hypotenuse, which using Pythagoras is square root of 5. Okay, so over here I'm going to have 2 alpha dot, and this will be 2 on root 5. Okay, this guy a little trickier to get rid of, okay, but you can use some trig identities to help you. I'm going to sort of skip ahead a little bit because it's not too hard to see that this should be, from memory, I think is a negative sine alpha, okay? Negative sine alpha. And you can go ahead and you can use this same trick here. Is it this one? No, hold on. You want to remember, like you've got, when you phase shift this, right, by pi on 2 radians, how do you turn that into sine? Because they're complementary, right? So I think, let me see if I remember this. Do it over here. Cos of x, right, is sine of pi on 2 minus x. Is that okay? So what I've got here is cos of x plus pi on 2. So I'll add pi on 2 to both. So that's sine of pi on 2 minus x plus pi on 2.
Yeah.
Is that right?
Yeah.
No, wait. It's x plus pi on 2 in place of x, so that actually should be a minus. Can you see that? I'll write it again with brackets to help you see it. I'm substituting, I'm actually not just adding pi on 2 to both things. I'm substituting it in for x. Okay, so this is pi on 2 minus x plus pi on 2. So it's a substitution, not just a phase shift, which is a bit different. Okay, so I've got cos of, I'll start writing alphas now because I want alphas. Alpha plus pi on 2, which equals sine of pi on 2 minus pi on 2 cancels. That's minus alpha. But sine is an odd function, right? So therefore this is minus sine alpha. Okay, so that's what I've done here. Content with that?
Yeah.
And I know what sine alpha is because it's opposite on hypotenuse. Oops. So I've got alpha dot pi, what did I just say? Minus 1 on root 5. That's going to be a 4 on root 5 and an alpha dot.
Yeah.
Okay. So now let's see, what shall I do? I'll multiply everything by root 5 because that's kind of a disaster, right? So I've got alpha dot plus pi with a minus sign at the front equals 4 alpha dot.
Yeah.
So let's rearrange a little bit. If I add, I'll just expand this out. Equals that. Right? So if I add this to both sides, I get 5 alpha dot equals negative pi. So alpha dot equals negative pi on 5. Which, by the way, totally makes sense because you're like, oh, it's getting smaller. Of course, it's getting smaller. It's going further around. At this particular instant in time, it should be, when it gets to here, it should start shrinking, right? Because it'll get to here, which is smaller. So that's why it's reducing.